Hey everyone, welcome to this explainer. I am so thrilled you're here. Today, we're throwing on our detective hats and diving into some essential grade 7 math standards. Specifically, we're going to crack the case of proportional relationships in the real world, targeting those core 7 RPA 2 and 3 standards. I want you to think of this not just as a math lesson, but as a genuine investigative case where we'll use data, evidence, and logical reasoning to solve a real-world multi-step mystery. So grab your metaphorical magnifying glasses because we are going to find out exactly how numbers behave when they are perfectly in sync. So here's the map for our investigation today. We'll start with the real-world challenge, find the unit rate, and then explore the table, graph, and equation. After that, we'll practice spotting the imposter, do a quick reasonableness check, and wrap it all up with a student self-check. Let's get right into it. All right, Section 1, the real-world challenge. Okay, picture this. You're at the grocery store, right? You see a massive bag of apples, and the sign says 5 pounds for $8.75. Sounds like a decent deal, but how do we scale down that bulk price to find a single consistent unit price? Like, what are you actually paying for exactly 1 pound? To crack this mystery, we need a very specific mathematical tool. And that brings us perfectly to the proportional relationship. Simply put, this is a relationship where one quantity is always a constant multiple of another. In our grocery store scenario, it just means the rate, the price per pound, stays exactly the same no matter how many pounds you toss in your cart. Whether you're buying 1 pound, 5, or 50, that underlying multiplier, it never changes. Moving on to Section 2, finding the unit rate. So how do we actually find this unit rate? Well, we follow a pretty straightforward 3-step process. First up, identify your input, which we call X, and your output, which is Y. For our apples, the pounds you put on the scale, that's your input, X. The total cost ringing up at the register is your output, Y. Step 2 is the magic calculation. We just divide the output by the input, Y divided by X. So we're taking our total cost of $8.75 and dividing it by 5 pounds. And finally, step 3 is identifying that result as our constant of proportionality, which mathematicians affectionately call K. And when you punch 8.75 divided by 5 into your calculator, you get $1.75. That right there is our calculated unit rate. It tells us that $1.75 per pound is our constant of proportionality, RK. For every single pound of apples you add to your bag, the total cost bumps up by exactly $1.75. All right, Section 3, table, graph, and equation. Let's map this out on a table to really see that constant multiple rule in action. If our input X is 1 pound, our output Y is 175. Double the input to 2 pounds, the output perfectly doubles to 350. And check out the bottom row. That's our original clue. 5 pounds gives us an output of 875. Every single input, when multiplied by our constant of 1.75, gives us the exact corresponding output. It is wonderfully consistent. And you know what? We can take that table data and easily translate it into a simple algebra equation, y equals 1.75x. This is a brilliant little formula because it represents our total cost, y, for literally any number of pounds, x. It fits perfectly into the standard proportional format of y equals kx. So if you suddenly needed 100 pounds of apples for some giant pie baking contest, you just plug 100 in for X, multiply by 1.75, and boom, you instantly know it's going to cost you $175. Now, if we were to graph this apple data on a coordinate plane, it has to follow some incredibly strict rules to actually be considered a true proportional relationship. First off, it absolutely must be a perfectly straight line. Second, and this is a big one, it has to pass exactly through the origin, which is the point 0, 0. I mean, think about it logically. 0 pounds of apples has to cost $0, right? If it doesn't cross at 0, it is not proportional, period. And finally, the graph will always feature the point 1, r, where r is our unit rate. So for us, that line is going to pass right through the coordinates 1 and 1.75. Next up, Section 4, spotting the imposter. Okay, we know what a perfect proportional relationship looks like, but let's compare our apple equation to a totally non-proportional situation. On one side, we have our apples, cost equals 1.75x, pure, simple, proportional. On the other side, we have an imposter taxi ride, where the cost equals 2x plus 4. Imagine this taxi charges a flat $4 starting fee just to sit in the back seat, plus $2 for every mile you travel. Now, both of these scenarios will create perfectly straight lines on a graph, but trust me, they behave very, very differently. Let's really interrogate this imposter taxi equation. The real issue here is that starting value of +4. That means before the driver even hits the gas at 0 miles, your cost is already $4. Because the graph starts at 4 and not 0, it completely misses the origin. And because of that starting fee, if you were to divide your total cost by your miles driven at various points during your trip, that ratio of y over x is going to keep changing. Sure, it's a linear function, but because that unit rate is not constant from the get-go, it entirely fails the proportionality test. Which brings us to Section 5, the reasonableness check. Whenever you're solving a multi-step application problem, you always want to run through a quick mental checklist. First, did you include your units? A number is really just a number until you label it dollars per pound. Interpreting your answer with units is actually a huge part of the standard. Second, ask yourself, does my graph actually start at 0? Third, does my equation, in that y equals kx format, actually match the unit rate I found? And finally, just step back and ask, does the real-world math make sense? If you calculate that 1 pound of apples costs $400, well, you've probably made a division error somewhere along the way. Always make sure your algebra mirrors the reality of the problem. And finally, Section 6, Student Self-Check. All right, time to hand the detective badge over to you. Here's a quick scenario straight from our linear function source material. Let's say a table gives you 3 coordinate points, 1, 5, 2, 10, and 3, 15. Your mission is to find the constant of proportionality. I'm going to pause for just a second so you can think. Remember our secret tool? Divide the output y by the input x. Did you get it? Well, if you divide 5 by 1, you get 5. Divide 10 by 2, you also get 5. And 15 divided by 3? Yep, still 5. So our constant of proportionality, k, equals 5. And if we wanted to translate that into an equation, it beautifully becomes y equals 5x. Fantastic detective work. To wrap up our case today, I want to leave you with one final thought to ponder. If you're looking at a graph and it's a perfectly straight line, but it crosses the y-axis at 3 instead of 0, is it a proportional relationship? Think back to what we just learned about that impostor taxi and the absolute rule of the origin. Keep that in mind as you continue exploring linear functions and proportional reasoning. Thank you so much for investigating with me today in this explainer. Keep asking those great questions, and case closed.